you fix a finite dimensional manifold and fix some geometric structure S, which should be Riemann structure, symplectic structure, compact structure, almost complex structure. And the question is, does S exist in N, in X? Or the very important geometric structure in information geometry. Riemannian structure, symplectic structure. Now, this question is first question. Now, another question. Assume that the structure S does not exist here. The question is the existence of foliation. That means a partition of manifold, of submanifold of the same dimension. So that in each submanifold, the structure X exists. So, the existence of S foliation. Foliation means a partition, a smooth partition, in submanifold of the same dimension. Example, in informative geometry, one can regard exponential model as some optimal model in some sense. If a model is not exponential, the problem, can you find foliation so that along the leaf of foliation, the model is exponential. Now, what is one of the goals of differential topology? It understands the geometry, transverse geometry or transverse topology of foliation. That means if you have a foliation, take your manifold X, it's a union of leaf. If a leaf is a submanifold of X of constant dimension. Remind that the partition may be smooth. This means that if you consider D equal to union of X, union of tangents space, this is distribution. And we need that distribution be differentiable, be smooth. Okay, now, there is some type of foliation which is particularly interesting. Riemannian foliation. When you have foliation, so you have two problems. Understand the internal structure of leaf. This is the intrinsic differential topology of leaf. And the problem is understand the transverse structure of leaf. If your foliation is nice, this is simple, then the space of leaf is manifold. In general, it is a topological space. When many topology, it is not Osloff. But you see, this is a manifold. The transverse geometry is the geometry of the space of leaf. Well, in general, this is not the case. Then, I will start the following question. Now, consider a connection. This is causal connection in your manifold X. Question. The existence of G, this is quadratic form. Such that nabla G equals 0. If the quadratic form is definite, then this is metric, it is Riemannian metric, or pseudometric, Riemannian metric in general. And this connection is metric connection. But even in singular case, the condition here tell you that the range of G is constant. Because this condition means that the parallel transformation preserve G. Since it preserves G, it preserves G. If you see the manifold is connected by R, then it is constant. Now, if the torsion of nabla is 0, then the kernel of G is in evolution. This means that the bracket of two sections is again a section. Then you define the foliation. And this is, we give you Riemannian metric, transverse Riemannian metric. It is metric, transverse to form. Then they give you Riemannian foliation. Riemannian foliation. My thought is concentrate to this question. This question. It is really whole question. It has been discussed by Thurston. In general, if this is definite, then the problem is the nature of the holonomy of this. Of this. And the general theorem, you can see Kobayashi Nomuzu tell you that this is metric if the holonomy is contained in orthogonal group. The orthogonal group. But I will discuss this question from two points of view. I will use the Amari Fonter. This means the conjugation we have to for this here. If you take a manifold, if you take Riemannian, you have nabla star, which is defined by G nabla star x, y, z equals x, G, y, z minus G, d, y, nabla z. We take some Riemannian metric and we take this transformation. The torque of sound is so that this is called this is that G star equals Z. This means that if you take a Riemannian structure, you take the connection with this thing, this is a symmetry in the space of connection. It is symmetry. Then what I call symmetry group, Riemannian group, is a group it generates, is a group of transformation in the space of connection, which is generated by Riemannian metric. What call it Riemannian group. I am interested in the dynamic, in the action of this group in the space of connection. At the other side, this is the first tool. The second tool is to consider the Tx star plus Tx. Sorry. Tx. Or this is the same thing as the homomorphism of Tx in Tx. Homomorphism of vector band. Of a vector band. And you consider the gamma, the section of this. This section is a Lie algebra. It's a form of Lie algebra, the self-section. And this is algebra of George's application. Now, you consider the George group. The George group is the open subset of this with a section which are inversible. Then these act on this group act in the set of connection. While you take element here, gamma, then nabla, gamma, is defined by nabla gamma x equal gamma nabla x gamma is 1 y. So and now if you take a connection, take a Riemannian structure and conjugate with this. And you associate with this a differential operator, D, nabla star, which is defined in this vector, or in this vector space, vector field, vector band. That bit, this operator, acts on the section of this one. This is defined by phi. This is equal. Yes, this is. Let me see. Yeah, this is phi. No, this is nabla star composed with phi minus phi composed with nabla. This is differential operator of the one. I will enter by the equation this equals 0. The system of partial differential equation of the one. So I will also this equation. This equation. And the theorem is this. That these are conformal equation of nabla or nabla G. Nabla G. We may write the equation G nabla star phi equals 0. And now on the other side, I have the Halleck's equation here. I have a Riemann group. This is abstract group which is generated by Riemannian metric in the space of connection. In the space of connection. Then you have an equation in the algebra of George application, and you have an abstract group with a general mathematic. I'm interested in at the other side. You have also the George group. Yeah, TX. Okay, these two groups, then you have two dynamics in the space of connection, the Riemann group and the George group. Now, I define some function. The data is in the paper. Then this work in how, not it, we'll let C, or no, K as causal connection in X. Then the two groups work here. The two groups work here. And then you have two moduli space. The space of isomorphism, that is the space K by this group, just Tx. And you also Ks X by the Riemann group. There is some relation between the two actions. One is to understand the actions. You saw this thing. The thing that is, when you have a manifold, a connection, you have this with metric G. Then we write this, that G. Now, if you take a J transformation, phi, or gamma, take gamma, an element here. Then you take nabla, gamma. No, nabla, the gamma act here also. Then you have here nabla, star, gamma. This is the conjugate of this one by metric G. G gamma. This is G gamma, this is A, B, G gamma A, gamma B. Okay, now, at the other side, if you take a second metric, take another metric here, G0, you have G0 star. And at the other side, if you have metric, this metric here, it is related to this one. You have some Jones transformation, 3, so that G0, A, B, equal G, C, A, B. You have some transformation like this. What this tell you? What this mean? And okay, at the other side, Okay, at the other side, what do you know? You know that you can also consider J, C, A, B equal G, C, A, C, B. Exactly not here. That's here. And the connection here, the connection here, is related in the conjugate of G by this method. What did it tell you? Did it tell you that if you take the orbit of nabla under the group, George group of Tx, if you take a Riemannian metric G, a connection, I'm sorry, you fix a connection, this connection, and you transform it by the metric, all metric standing in the same orbit. Yeah. This orbit. Didn't mean that the group generated by the metric here act on the modular space of the connection modulo the George transformation. And in this space, when you take a class of connection, you consider it isotropy stability subgroup. You consider a subgroup here. This is Riemannian group. You consider it stability subgroup. But okay, this is infinitely general group. General group. Now, when you take an element here, you have the length of this element in the group. And you write that you consider S nabla equal the minimum when gamma back here, no gamma of the length of gamma. And use 1. And the theorem is this integral is an invariant. It is an invariant of this orbit. And it is the only obstruction, it is an obstruction for the connection being metric. The connection metric is and only if this is 0. Now, if it is not 0, I don't know. I have no interpretation of this. I have no interpretation. Now, I discussed the same problem. I discussed the same problem from the viewpoint of this differential equation. Upon this differential equation. And the theorem is that the theorem, this equation is linear equation. Linear equation is that if phi is solution to the equation to 1, what means that phi equation to 1? It means that you have nabla star x phi the y equal phi the nabla y. What does this mean? And now, you consider, we take a solution like this, and they exist in the solution, they exist 5 and 5 star, where also solution to 1, to the equation 1, are having the following property. The first property is that if you take half of G phi x, phi A, B, plus G A phi B, this is equal G phi A B. And if you take this G, the same thing here, take here, and this equal G phi star A B. And okay, this is equal Q A B, and this is omega the A B. This is a differential two form, and this is a quadratic form. Both have the property that nabla Q equals 0, and nabla omega equals 0. So if omega is nabla is torsion free, you have here a symplectic foliation and Riemannian foliation. This means that, so this solution, this equation also controlled differential topology. That means Lagrangian, not Lagrangian, Riemannian foliation or manifold, Lagrangian foliation or manifold. The impact of informational geometry here is that all Riemannian foliation can be obtained by this way. This is not known in differential topology. Poppy study Riemannian foliation, but in general, there is no way to say that Riemannian foliation exists. You say, give a manifold, I consider Riemannian foliation, and so on. And this is also a whole problem. The point is, after you can't find this exercise with Abraham Marsden, something like this. Take a family, take a foliation, and suppose that every leaf of a foliation is a symplectic manifold. This means that in every leaf you have symplectic structure. Question: you want to know if there exists in a manifold differential two form. What restrictions are your symplectic structure on the leaf? The question is that all can be constructed using this formalism. Yeah, okay. Now, so you also have answer to know this control also the symplectic geometry, the existence of symplectic structure in manifold. What you need solution with maximal rank of this. Here. And if the rank is not maximal, okay, yeah, you have solution. That is, this rank is, this will give you an optimal model of symplectic foliation in the manifold. Okay, I finished with this. I'm sorry.
Okay, short question.
Yeah.
So let's thank all the speakers with this question again.
Thank you.